Assalamualaikum warahmatullahi wabarakatuh. My name is ASHIKA binti MARZAIRI and this is my teammates.
Hi, my name is NURUL binti IBRAHIM.
My name is SYAZWANIE binti ZAINON.
We are from Mathematics 3, PPISMP 2025-2026, and today we will be presenting our pre-calculus coursework, which is a video essay presentations. So, I will be your moderator for today. Shikin will be panel 1 and Wani will be panel 2. First of all, thank you for joining our discussion session for today. We are happy to have the opportunity to share and discuss an interesting mathematical topics that has real-world applications. Today, our discussion will focus on optimizing drones delivery route using differentiations. In recent years, drones technology has become increasingly important in many industries. Drones are used in fields such as agriculture, surveillance, transportation, environmental mentoring, and logistics. However, one of the most meaningful applications of drones today is in healthcare sector, especially in delivering medical supplies to remote areas. In many parts of the world, there are locations that are difficult to reach using traditional transportation methods. These places may include remote islands, mountainous regions, or rural communities with limited infrastructures. In such situations, drone can provide a faster and more efficient delivery system. For example, drone can be used to deliver vaccine, blood samples, emergency medicine, or other medical supplies. However, even though drones offer many advantages, there are also limitations. One of the biggest challenges is the battery life. Drones rely on battery for power, and this battery have limited capacity. Therefore, drones cannot travel indefinitely without recharging. Because of these limitations, it is very important to plan drones route carefully in order to minimize the energy consumptions. In this scenario we will discuss today, a drone needs to deliver a medical supplies from a mainland base station to a remote island. However, there is an important condition in the situations. Flying over the water would cause the battery to drain 20% faster compared to flying on the land. Because of these differences in battery consumptions, the drone cannot simply choose the shortest route. Instead, the drone must choose the route that is used the least battery energy. To solve this problem, we can use mathematical concepts, particularly differentiations, which is a topic in pre-calculus used to find optimal values. Today, we will be exploring how mathematical thinking can help determine the most efficient route for the drones. Before we move into the deeper discussions, I would like to hear some opinions from our panel today. So, panel 1, what are your thoughts about the use of drones in medical delivery?
In my opinion, the use of drone in medical delivery is a very important technological advancement. In many emergency situations, time plays a crucial role. Patients who require urgent medical treatment may not have the luxury of waiting for traditional delivery systems. For example, if a patient on a remote island needs urgent medication, it may take a long time for a boat to reach the island, especially if weather conditions are not favorable. However, drones can travel directly through the air and reach the destination much faster. This makes drones extremely useful in situations where speed and efficiency are essential. Furthermore, drones can also reduce transportation costs in some cases because they do not require complex infrastructure such as roads or bridges. However, drones also face several technical challenges. One of the most significant challenges is battery capacity since drones rely on batteries. Their flight time is limited. If the drone does not manage its energy efficiently, it may not be able to complete its journey. Because of this reason, careful planning of the drone's flight path becomes very important.
I would like to hear from another perspective. Panel 2, what is your opinion about the scenarios?
Thank you, moderator. I agree with panel 1 that drones have great potential in improving delivery system, especially in healthcare. However, this scenario that we are discussing today becomes particularly interesting when we consider the difference in battery consumption between flying over land and flying over water. At first glance, many people might assume that the best route for the drone is simply a straight line from the mainland to the island. After all, in geometry, the shortest distance between 2 points is a straight line. However, the situation becomes more complicated When we consider that flying over water consumes more battery power, this means that even though the direct route is the shortest distance, it may not be the most energy efficient route. Instead, the drone must carefully balance two factors. First, the total distance traveled, and second, the energy consumption associated with different type of terrain. This is where mathematics become extremely valuable. By constructing a mathematical model, we can analyze different possible routes and determine which route maximize the total battery usage.
That is a very thoughtful explanation. Your point clearly shows that sometimes the most obvious solutions is not necessarily the best solutions, right?
Yes.
This situation is actually quite common in many real-life problems, where multiple factors must be considered before taking a decision. Mathematics provides us with a tool to analyze such as logically and systematically. Now that we have introduced the scenarios and it is important, let us move to the next part of the discussions. Before we focus on the mathematical aspects, it may be helpful for us to briefly discuss the development of drones technology. Panel 1,
Yes.
could you explain to me how drones are used in modern industries?
Yes, certainly. Over the past decade, drone technology has advanced significantly. Originally, drones were mainly used for military purpose. However, today they are widely used in many civilian applications. For example, in agriculture, drones are used to monitor crops, spray pesticides, and collect data about soil conditions. In environmental science, drones are used to monitor wildlife, track deforestation, and observe climate changes. In logistics and transportation, companies are experimenting with drone delivery systems to transport small packages quickly and efficiently. Perhaps one of the most impactful applications is the healthcare sector. In some countries, drones are already being used to deliver blood supplies, vaccines, and medical equipment to remote clinics. These deliveries can significantly reduce transportation time and improve access to healthcare services.
It is clear that drones technology has many practical applications in various industries. Panel 2, do you think drones technology will become more common in the future?
Yes, I believe drone technology will continue to grow rapidly in the future. As technology advances, drones are becoming more efficient, more reliable, and more affordable. Researchers and engineers are constantly working to improve battery technology, flight stability, and navigation systems. With this improvement, drone may eventually become a regular part of transportation and logistics system. However, in order for drones to operate efficiently, it is important to optimize their performance. This includes optimizing their routes, energy consumption, and delivery strategies. Mathematics play an essential role in solving this optimization problem.
This shows that mathematical optimization is not just academic exercises, but it is an important tool for improving modern technologies. Now that Now that we understand the background and the potential of drones technology, let us focus on the core challenges in today's scenarios. We are dealing with a non-routine problem, delivering a medical supplies to a remote island, while considering that flying over water drains 20% more battery energy, than flying over land. Panel 1, can you explain why this problem is considered a non-routine?
This problem is non-routine because it does not have a straightforward standard solution, unlike typical delivery problems where the shortest distance is always the best. Here we must consider both distance and energy consumption. The complication arises from the fact that flying over different terrains has different energy costs. Flying over water is more taxing on the battery than flying over land, which introduces a variable factor into route planning. This requires a deeper level of thinking as we cannot simply rely on basic geometric intuition. We need to use mathematical modeling and calculus to analyze multiple possible routes and to determine which one uses the least battery usage.
The non-routine aspects makes this problem a great example of how mathematics can be helped in discussion makings, right?
Yes.
It shows that sometimes the most obvious choice, such as taking the straight line, may not be optimal. Instead, we need to use systematically evaluation alternative and use mathematical tools to find the best solutions. Panel 2, I would like to hear your opinion. Would you like to add anything?
Yes, moderator, I would like to highlight that non-routine problems like this often reflect real-world complexity. In practice, engineers and logistic planners frequently encounter situations where multiple factors interact. By modeling the problem mathematically, we can simulate various scenarios and identify the route that optimize battery usage. It's particularly important in critical applications like medical supply delivery, where efficiency can be a direct impact on human life.
Panel 2, your point reinforced the idea that mathematical analysis is not just theoretical, it has practical and life-saving implications. Before we move on into the calculations, it is helpful for us to visualize the problem. Panel 1,
Yes.
how can visualization help us understand the scenario better?
Okay. Visualization is essential because it allows us to see the problem in a spatial context. We can draw a map showing the mainland base, the remote island, and potential routes. We can also indicate area of land and water and visually represent the difference in energy consumption over each terrain. This helps in understanding how the drone's path might be adjusted to conserve battery. For instance, a route that initially seems longer might actually be more energy efficient if it reduces the distance flown over water.
Yes, a clear diagram can help everyone, engineers, mathematicians, and even non-technical people, to understand the trade-off involved in routine planning. Panel 2, do you have any additional insight about the visualization?
Certainly, in addition to static diagram, we can also use dynamic simulation. This simulation allows us to model how the drone's battery depletes over time depending on theories. By visualizing energy consumption dynamically, we can better predict whether the drone can reach its destination safely or if alternative routes are needed. This approach makes the abstract concept of the energy optimization more concrete.
Visualizations, both statics and dynamics, bridges the gap between the abstract mathematical concepts and practical applications. Now, let us explore the geometry and distance concept involved. Panel 1, could you explain to me the role of geometry in the scenarios?
Okay, so geometry provides the foundation for understanding distance between points. The shortest distance between 2 points is a straight line, which is the concept we often start with. However, in our scenario, geometry alone is insufficient. While a straight line distance might be the shortest, it does not consider varying energy consumption over different terrains. This requires integrating geometric understanding with additional information about energy cost, which is where mathematics, specifically calculus, come in.
So, geometry gives us the big structure, but we need to find the optimal path. So, panel 2, how can we use the geometric concepts along with the energy considerations?
We can combine geometry with distance. Each segment of the routes can be assigned as a cost depending on the theories. For example, 1 kilometer over the line could be counted as 1 unit of energy, while 1 kilometer over water could be counted as 1.2 units. By doing this, the geometric routes is adjusted based on energy efficiency, and the optimal paths may curve or zigzag to minimize battery usage. This approach turns a simple geometric problem into a more realistic and solvable model.
Precisely, weighted geometry allows us to consider multiple factors simultaneously, leading to a solution that is both mathematically sound and practically viable. Now, let us introduce the idea of variables, which is essential for building a mathematical understanding of the problem. Panel 1, could you explain to me how variables come into play here?
Thank you, moderator. In this scenario, variables allows us to represent different aspects of the drone's journey. For example, we can define a variable for the distance the drone travels over land, another for the distance over water, and a function that represents total battery energy consumed based on these distances. By using these variables, we can analyze how changes in the route affect energy usage and explore which combination of distance will minimize battery consumption.
Okay, thank you, panel 1. By structuring the problems with variable, we make a real-world situation more analyzable and manageable, right?
Yes.
I would like to add that we could also consider variables beyond just distance. Factors like the drone speed or the extra drain when flying over water can also be included. These additional variables make the model more realistic. reflecting how energy consumption varies under different conditions.
Breaking down the problems into variables allows us to address a complex scenarios in a structured and a logical way.
Of course, mathematical modeling helps us to translate the scenario into a form we can analyze. By defining how much energy the drone uses per kilometer over land and over water, we can build a function that calculates total energy for any route. Once we have this function, we can examine different routes to see which one minimizes battery use. Modeling in this way turns an abstract scenario into a tangible problem we can solve mathematically.
A mathematical model gives us the ability to make objective comparisons and find the solutions based on analysis rather than intuitions.
Exactly. Without a model, we might guess which route is best. With a model, we can quantify energy usage, stimulate different routes, and make decisions grounded in data.
Now, let's focus on specifically the battery consumptions. Panel 1. How does this affect the choice of the route?
Okay, energy consumption is a critical factor. A route that seems shorter may not be optimal if it involves a longer distance over water. So because the drone will drain its battery faster. So this means that sometimes a slightly longer path over land could save more battery than the straight line across water. So it shows that efficiency isn't just about distance, but it is about how energy is used in different conditions.
Okay, optimizing a route is about balancing multiple factors, not just choosing the shortest path, right?
Hmm.
Okay,
Yes.
thank you. I'd like to add that knowing that drones' battery capacity and how energy consumption changes over terrain allow us to plan safely. We can stimulate different routes and predict whether the drone can complete the journey. This ensures that energy is managed efficiently while avoiding the risk of running out battery mid-flight.
Excellent point, panel 2. Understanding the technology's limitation is the key to making informed decisions. Finally, let's discuss differentiations and its role in route optimizations. Panel 1, could you explain?
Okay, differentiation is a powerful tool because it helps us to find the point where a function reaches its minimum and maximum. So in this scenario, the function represents the battery consumption depending on the drone's route. By taking derivatives, we can identify the exact distances over land and water that minimize energy usage. This allows us to determine the most efficient path for the drone mathematically.
So differentiation transform a best choice problem into a
Yes.
precise calculation that we can analyze,
Yeah.
right?
It also allows us to understand how smart adjustments in the routes affect energy consumption. Even minor changes can increase or decrease battery usage, and derivatives provide a way to fine-tune the routes for optimal efficiency.
This demonstrates how pre-calculus is a practical tool that connects mathematical theory direct to the real-world problem solving. Having explored differentiation and its role in finding the minimum energy path, let's talk about the optimization more broadly. Panel 1, how do you see the concept of optimization applying to our drone scenarios?
Thank you, moderator. Optimization in the context is about to finding the route that allows the drone to complete its delivery using the least energy. So while still reaching the destination safely, it is not just a single calculation. It is a process of balancing several competing factors. For example, the distances over land versus water, battery limitations, drone speed, and even potential environmental conditions like wind. The derivative gives us a starting point, but optimization considers the bigger picture. For instance, sometimes the mathematical minimum may suggest a path that passes very close to a no-fly zone or over rough terrain. Optimization then integrates these real-world constraints to adjust the route practically.
So optimization is really about translating the mathematical solutions into a feasible, safe, and more efficient routes. Panel 2, would you like to explain on that?
Absolutely, optimization is iterative. Once we have the energy function and its derivative, we can test different parts, slightly adjusting distance over land and water, and see how energy consumption changes. This iterative approach mirrors what engineers do when programming autonomous drones. They don't just rely on single formula, This stimulates multiple routes, adjust parameters based on constraints, and select the route that balance efficiency and safety. Optimization thus become a dynamic, real-world application of mathematical analysis.
An important part of understanding optimizations is visualizing it. Panel 1, could you explain how graphing can help interpret these energy functions?
Certainly. Imagine plotting the energy function on a 3D graph with the x-axis representing distance over length, and the y-axis distance over water, and the z-axis representing the total battery consumption. So the surface forms a kind of landscape. The point where the surface reaches its lowest height corresponds to the minimum energy consumption, the optimal route. Graphs allows us to see how energy changes when we move in different directions, revealing values and regions that indicate more and less efficient paths.
That is a very intuitive way to explain it. So panel 2, can graph also show sensitivity or risk in energy consumptions?
Yes, by examining the slope of the surface, we can see which directions are steep and which are flat. A steep slope indicates that even a small deviation from the optimal path significantly increases energy use, which is risky. A flatter slope indicates that slight deviations are less costly. This type of analysis is extremely useful in real-world planning because no drone can follow a perfect path. There are always a small adjustment needed due to the wind, GPS, error, or obstacles. Graphical interpretation help identify which routes are more forgiving and reliable.
Now that we discussed optimization and visualizations, let us analyze the routes itself. Panel 1, how would you approach this route analysis in these scenarios?
Route analysis involves examining multiple potential paths and comparing their energy costs. We might we might consider a direct line over water that hugs the coastline for part of the journey, or a path that detours slightly inland. By calculating or simulating energy consumption for each, we can determine which route minimizes battery usage. This analysis often reveals surprising results. For example, a longer distance may be more efficient if it reduces time spent flying over water.
Yes, panel 1. It highlights the importance of thinking beyond the obvious shortest path. Panel 2. What other factors might we consider in route analysis?
We should consider environmental variables such as wind and potential obstacles. Wind can either assist or hinder the drone, altering energy consumption. Temperature can affect battery efficiency, and obstacles may require sudden deviation. In addition, reliability and safety are important. Even if a route consumes slightly more energy, it may be preferred if it reduces the risk of drone failure. In practical application, energy optimization must be balanced with operational safety and feasibility.
Finally, let's consider the alternative scenarios. Panel 1. Why is it useful to explore what ifs scenario in drones routing planning?
So, exploring alternative scenario allows planners to anticipate challenges and adapt solutions. For example, what if part of the land routine becomes inaccessible due to weather? What if the drone must carry heavier cargo? By analyzing these what if scenarios, we can test the robustness of our optimal route. Differentiation and energy modeling provide the baseline optimal path, but alternative scenarios help ensure that the plan is resilient under real-world uncertainty.
Exactly, panel 1. Optimization is not static. It must consider variability and expected conditions. Panel 2. Could you give an example of such alternative scenarios?
Imagine a scenario where the drone must deliver multiple packages to different islands. Now, we have multiple destinations, varying payloads, and possibly limited recharging options. The principle we discussed, variable, energy modeling, differentiation, and optimization, still apply, but the problem becomes multi-dimensional. We may need to incorporate algorithmic planning methods like route rescheduling or gradient-based optimization for multi-stop deliveries. Another example could be changing battery efficiency over time and due to wear and tear. A route that was optimal yesterday may no longer be optimal today. Considering this scenario, ensure flexibility and reliability.
Insightful panel 2. This reinforced that mathematics and engineering must work hand in hand. Optimization provides a clear target, but real-world application demand flexibility, robustness, and adaptive planning. Now that we've explored optimizations and alternative scenarios, let us discuss energy efficiency in a broader sense. Panel 1. Why is the energy efficiency so critical in drone operations?
Okay, so energy efficiency is central because battery life is the limiting factors for almost all drones. Unlike vehicles, unlike vehicles powered by fuel, drones rely on batteries that have finite capacity and battery weight also affect flight performances. An efficient route does more than just conserve energy, so it allows drone to carry heavier payloads, fly longer distances, and even perform multiple deliveries without recharging. In the medical context, this efficiency can directly translate into life save because critical supplies reach their destination faster.
Indeed, panel 1. Energy efficiency is not just abstract goals. It has immediate, tangible, and consequences. Panel 2, would you like to expand on that?
Yes, moderator. Efficiency also affects sustainability and operational costs. By minimizing non-important energy usage, drone operators reduce battery wear, lower maintenance costs, and extend drone lifespan. Moreover, in larger scale logistic network, small improvement in energy efficiency per flight can scale up to massive saving in energy, time, and operational results. This is why optimization and careful route planning are essential not only for individual drones but also for entire fleets.
Now, let's connect our discussion to real-world applications. Panel 1, how is this kind of route optimization used today?
In healthcare, some countries are already using drones to deliver blood supplies, vaccine, and medical equipment to remote clinics. These systems rely heavily on route planning, and energy management to ensure timely delivery. Beyond healthcare, energy optimized routes are also critical in agriculture, where drones spray crops over large fields, in search and rescue missions, and even in urban package delivery. In each case, understanding terrain, energy consumption, and drone capabilities allows operators to plan effective and reliable operations.
So, the principles we're discussing are not hypothetical. They are actively shaping emerging technologies. Panel 2, can you comment on applications beyond drones?
Similar optimization principles are applied in autonomous vehicles, electric delivery trucks, and even robotic warehouse systems. Any system where efficiency is constrained by energy or time benefits from mathematical modeling, differentiation, and optimization. For example, in smart case, route planning for delivery vehicles or service robot must consider battery limitation, traffic condition, and operational prioritize. The same concept of modeling, sensitivity analysis, and interactive optimization apply.
Panel 1, from an engineering perspective, how does this mathematical framework support technology development?
Okay. Mathematical modeling and optimization provide engineers with tools to test design before deployment. For instance, understand how energy consumption varies with route characteristics inform battery design, motor efficiency, and payload capacity. By integrating mathematical model into simulation software, engineers can predict performance under different conditions, identify bottlenecks, and optimize hardware and software together. This reduces the need for costly trial and error in real-world testing.
Okay. Panel 2, any thoughts on how technology improvement interacts with mathematical models?
Yes, as technology advances, better battery, light material, more efficiency motor, the mathematical model must updated to reflect these changes. Optimization is an ongoing process. The model provides a framework, but as technology evolves, the optimal routes, energy calculation, and operational strategies evolve too.
Even with sophisticated models, there are limitations. Panel 1, what should we be conscious about?
Models are simplification of reality. For example, our current discussion assumes a constant rate of battery usage over land and water. But in reality, wind, weather, and terrain irregularities can change energy consumption significantly. Additionally, the model assumes continuous adjustment of the route, whereas drones may have discrete waypoints. Human errors, hardware malfunction, and environmental unpredictability also introduce uncertainty.
So model provide guidance, but cannot capture every real world factor, right? Panel 2, can you add to this?
Yes, another limitation is scalability. A model for a single deliver may not translate directly to multiple drones or multiple stop deliveries without further adjustment. Computational complexity and data availability can also constrain the accuracy of large-scale simulation. Despite this limitation, models remain invaluable because they offer a structured, rational approach to complex problems.
Looking ahead, how can we improve this model, Panel 1?
We can incorporate more variables to reflect real-world conditions, wind patterns, temperature fluctuations, drone payload variations, and battery degradation over time. Machine learning could be integrated to adapt routes dynamically based on previous flight data. Future research might also explore swarm optimization, where multiple drones coordinate to optimize energy collectively, or real-time adaptive routing that responds to environmental changes mid-flight.
Panel 2, do you see other optimization directions?
Yes, incorporating AI for predictive analytics and adaptive control is very promising. Also, interdisciplinary research combining mathematics, engineering, and data science will improve both model accuracy and operational efficiency. Okay. This ensures that optimization is static but evolve as the drone ecosystem become more complex.
Before we conclude, let's reflect. Panel 1, what is the main takeaway of these discussions?
Okay. Mathematics is a powerful tool for solving practical problems. Even a simple concept like differentiation can have profound implication when applied systematically. By combining theory with simulation and real-world constraints, we can design efficient, reliable, and safe systems.
Panel 2, what about you?
I would like to add the discussion highlight the importance of an integrated approach. Optimization is not only about formulas, it's about understanding technology, environmental factors, and operational realities. The ability to model, analyze, and adapt is crucial for any engineering application.
To wrap it up, this discussion demonstrates how a combination of mathematical reasoning, engineering insights, and practical planning can solve complex real-world problems. Panel 1, what is your final thoughts?
The journey from defining variables to differentiation, optimization, and root analysis shows that simulating abstract mathematics has very tangible outcomes. Efficient drone delivery isn't just about flying, but it is about strategic planning informed by rigorous analysis.
Panel 2, any thoughts?
This discussion illustrates the broader impact of mathematical modeling beyond roads. It teaches us to think critically, evaluate alternatives, and make informed decisions. These skills are essential not just in technology, but in any fields where resources are limited and efficiency is critical.
Okay, thank you both of you today for the discussion that we have. Today's session shows that careful mathematics analysis combined with engineering and practical insights can optimize not only drones delivery routes, but also a wide array of real-world systems. The principle we discussed, variables, modeling differentiations, optimizations, and adaptability, form a bound for solving complex challenges in modern technology. So that is all from us today. Thank you.